Welcome back, folks, to another very exciting chemistry video for today. Today, our focus is on a very important topic. That is, we are going to be discussing molecular structure and shape. So what that means is that we are going to dive into the nitty-gritty details about drawing Lewis dot structures, looking at something known as Vesper Theory, which determines molecular geometry. We're also going to discuss hybridization, as well as determining the formal charge on atoms to determine which Lewis structure is most likely to be accurate. Now, if you have not done Lewis structures or molecular geometry before, I would highly recommend that you go and watch one of my other videos, either in my chemistry series or my chemistry 2 series, because we're going to assume that you already have the basic knowledge of how to draw these. We're just going to dive into a little bit more detail or possibly work a little bit faster than what we normally would in a regular chemistry class. So if you're unfamiliar with these concepts and haven't discussed these before, I'd highly recommend you check out one of my other videos before moving on. For the rest of us, let's move on. So hopefully by the end of this video, you're going to be able to draw all Lewis dot structures and diagrams. You should be able to draw Lewis diagrams for complex organic molecules, understand when resonance structures occur and how that impacts bond strength and length, use formal charge, determine how Vesper theory uses Coulombic repulsion of electrons around a central atom, infer about molecular geometry, bond angles, energy of bonds, length of bonds, polarity based on Lewis dot structure, and describe the hybridization of the central atom. So again, if you've taken chemistry classes before, this should all look very familiar to you. However, we're going to dive into a little bit more detail than probably what we've seen in previous chemistry classes. Let's get started. So first off, let's take a look at a Lewis dot structure. And Lewis dot structures are diagrams that simply show the bonding between atoms in molecule and lone pair. So what this simply represents is the electrons around the atom and which electrons are either paired in bonded pairs or which exist in lone pairs. Now, how we draw these is very important because we need to make sure, first off, that all of our octet rules or duet rule, if we're looking at hydrogen, are satisfied. Now, as always, there are going to be some exceptions to this, which we will talk about a little bit later on. Secondly, we also need to make sure that we have the correct number of electrons in our structure that match up the total number of valence electrons when we add up the valence electrons of the individual atoms combined together. So, for example, in this structure, we should have a total of 16 valence electrons. Carbon brings 4 to the table based on its location on the periodic table, and each sulfur brings in 6. So it's important to understand that we need to make sure that we use rules that fit those two criteria, that all of our octet rules are satisfied with the few exceptions, of course, and that we are ensuring that we have the correct number of valence electrons in our structure. So how we do that is by following the steps. And I can promise you, if you follow the 6 steps that are listed on the next slide, odds are you will never get a Lewis dot structure incorrect. So here are our 6 steps. And again, please write these down. These are very important for you to make sure that you understand. First, we need to count out the total number of valence electrons in the structure for each atom. So what we do is we take a look at each individual atom, we look at the periodic table, and based on their location on the periodic table, we determine how many valence electrons they're going to bring to the Lewis dot structure. Again, we are going to use periodicity as a way to determine how many valence electrons are going to be in each atom. So in the first column on the periodic table, 1 valence electron. Second column, 2. Skip our D block. Third column, 3, fourth column 4, and so on until we get to our noble gases, which bring 8 to the table. Step number 2 is to make your least electronegative atom your central atom, except for hydrogen. Hydrogen doesn't typically exist as a central atom because it can only bond a maximum of 1 time. So our least electronegative atom, remember that electronegativity is highest up and to the right, and so we want to find that individual atom in our compound that is furthest away from fluorine. Step 3 is to single bond everything to your central atom and add lone pairs of electrons to satisfy your octet rule except for hydrogen. So we're going to single bond everything to our central atom. Again, a couple exceptions for this we'll talk about in a moment. And then add lone pairs to satisfy your octet rule. So if something is single bonded, we're going to add 6 electrons on the outside because that's going to give it a total of 8. 2 electrons in the bond, and then 6 electrons that are in the lone pairs. Step 4, we're going to count the total number of electrons in your structure, and if they match the total number that you came up with in step number 1, then you are done. If there are too many electrons, we need to take away 2 lone pairs, one from one atom and one from another, and add a double bond between them. And you're going to continue to do so until you have the correct number of electrons. What that does is that keeps the octet rule satisfied and reduces the total number of electrons in your structure by 2. So you'll see what I mean as I go through and show you a couple of sample problems. But again, these 6 steps are really important because if you follow these 6 steps, there's very little chance that you're going to make a mistake. So let's draw some Lewis dot structures. First, let's take a look at carbon dioxide, a very simple molecule. Again, CH3F, again, a very simple molecule, but again, following these 6 steps is going to ensure that you get these correct every single time. So the first thing we're going to do is count up our total number of valence electrons. Each carbon brings 4 valence electrons to the table, while each oxygen brings 6. So we add those up, and we know we're going to have a total of 16 valence electrons in our structure. So our next step is to determine what our central atom is going to be. We're going to attach single bonds and then satisfy the octet rules around each individual atom. So our central atom is going to be carbon because if I look at the periodic table, carbon is further away from fluorine than oxygen, therefore it has a lower electronegativity. So we're going to use that as our central atom. So I go ahead and draw out my basic Lewis structure. My carbon is my central atom. I single bond each oxygen to my carbon, and then I add lone pairs all around them to satisfy the octet rule. So notice I added 6 electrons around each oxygen in order to give it a total of 8. And then I add 4 electrons around carbon to give it a total of 8. So again, the whole goal here is to just add those lone pairs until you satisfy the octet rule for every single atom in your Lewis dot structure. Now I'm going to count up the total number of electrons in my structure and see if that's equal to 16. And I find out that I have 20 valence electrons in my structure, which unfortunately, that is too many. So as a result, we're going to remove 2 lone pairs of electrons. I'm going to remove 1 from carbon and 1 from oxygen, and then I'm going to add a double bond in between them. So again, what that does is that keeps the octet rule satisfied, but yet reduces the total number of valence electrons in my structure by 2. So now I go ahead and recount the total number of electrons, and I find out that I have 18. Well, that's still too many. So in order for the sake of symmetry, what I'm going to do is I'm going to remove a lone pair from carbon and remove a lone pair from the other oxygen atom. And again, what that's going to do is that's going to keep the octet rule satisfied. Notice that carbon still satisfies the octet rule along with each oxygen by doing this. I count up the total number of electrons in my structure and I find out that I have 16, and therefore I have correctly drawn the Lewis structure for carbon dioxide. Let's do another example with CH3F. And again, we go through and we count up the total number of valence electrons in our structure. Carbon has 4, each hydrogen has 3, fluorine has 7. So we add them up and we get a total of 14 valence electrons in our structure. Once we have done that, we're going to determine our central atom, which again is the furthest from fluorine. In this case, it is carbon once again, because remember, we don't include hydrogen in our central atom discussion. So now I'm going to attach all of my other atoms to my carbon in my structure with single bonds, and then add lone pairs around to satisfy the octet rules. So in this case, each hydrogen is attached, but remember, each hydrogen only wants 2 valence electrons in its outer shell. So as a result there, we are good. And then fluorine requires 8, so we're going to add 6 valence electrons, or 6 lone pairs of electrons. So again, same process here. I'm going to count up the total number of electrons I put into my structure. If it's 14, I'm done. If not, I need to take away 2 lone pairs and add a double bond. So I count them up, 2, 4, 6, 8, 10, 12, 14. I count up that I have 14 electrons in my structure, which is the same as what I counted at the beginning. So therefore, I am good. So again, as you follow all 6 of these steps, it starts to become second nature. You don't think about them individually as steps, but just as a process as a whole. But again, following those steps is absolutely key to ensuring that you draw correct Lewis dot structure. So let's talk a little bit about some more complex Lewis dot structures. That is, ones that may not necessarily exactly fit the mold of the 6 rules that we've talked about. So let's say you draw out your Lewis structure and you actually find out that you have fewer electrons in your Lewis structure, despite all the octet rule being satisfied, than what you counted at the beginning, meaning that you have some electrons left over from step 1 that you didn't end up getting in your structure. Well, you're just simply going to add those to your central atom. And that's where we get some more complex Lewis dot structures that don't necessarily satisfy the octet rule. For example, sulfur is a great example of an element that typically cannot satisfy the octet rule with just 8 in its outer shell. It can have 10, it can have 12. Same thing with things like xenon and even argon. Complex structures tend to be written as you would draw the Lewis structure. So for example, if you look at the diagram on the right here, this would be written as CH3OH. So if you think about that, CH3, you can break that, like if you split that right down in the middle, you have your CH3 on the left side and then your OH towards the end. So carbon structures tend to be written as you would draw the Lewis dot structure. So you see what this is a little bit more in practice, but complex structures, especially carbon structures, tend to form long chains of carbons that are surrounded by hydrogen. So if you see something like C8H18, basically you're going to draw 8 carbons in a single line and then add hydrogens all around the outside. Let's say we have an ion, so for example, NH4 plus or NO3 minus. Well, if we have a plus charge, that means we have one less electron in our structure than what we would count. So NH4 plus, you're going to subtract an electron from step number 1. And let's say you have NO3 minus. If you have NO3 minus, you're going to add an electron to that very first step. For this class in particular, we're primarily going to be looking at Lewis dot structures that have even numbers of electrons. So for example, NH4, you would think would have 9 in its structure. Well, that doesn't make sense, but if you think about it, NH4 plus is going to have one fewer electron or one less electron, so it's going to have 8 electrons in its structure. So make sure you're thinking about those ions and those charges, because that's going to help you determine the correct number of electrons in that first step, which is going to help you as you go through and draw your Lewis dot structure. So let's look at a couple of examples of complex Lewis dot structures here. We have SF4 and CH3, CH2, NH2. So a little bit more complex than what we've looked at previously, but again, think about those rules we've just talked about as we go through and look at these examples. So SF4, we count up the total number of valence electrons just like what we've done previously, and we are going to have 34 total valence electrons. So I go through and determine my central atom, which is going to be sulfur, because sulfur is further away from fluorine than fluorine is. Makes sense. So I draw my basic Lewis dot structure here. Sulfur is my central atom. I single bond everything to my central atom. I satisfy the octet rules for all of my fluorines by adding 6 lone electrons on the outside of each individual fluorine. Well, I count up the total and I actually get 32 electrons. Well, 32 electrons is not enough. I need 34 electrons in my structure. I have 2 electrons left over. So as what we've previously discussed, you're just going to add those to your central atom. So this is an example where sulfur does not satisfy the octet rule. Instead of having 8 in its outer shell, it now has 10 in its outer shell, and that is perfectly okay in certain circumstances, such as the one that we've just taken a look at. So if we have extra electrons, we just simply add them to our central atom. So simply what you're going to do at the very end, just like what we've discussed, is going to add that lone pair to your central atom, and that's where you get your right answer. Let's look at the next problem, CH3, CH2, NH2. So I count up the total number of electrons in my structure, just like what I've done previously, and I know I need to have 20 in my Lewis dot structure. Well, again, if we break this down into individual parts, I've got a CH3 part, a CH2 part, and an NH2 part. So again, you break it down into its individual steps. Keep in mind, this Lewis dot structure is going to be drawn very similar to how it is written as a structure itself. So notice what I've done here. I've got my CH3 part on the left, my CH2 part in the middle, and then my NH2 part. Notice that H's aren't going to be bonded to each other. Typically, the hydrogens in these types of compounds are on the periphery. They're on the outside of the structure. So the carbon's going to be bonded to the following carbon, which is going to be bonded to the following nitrogen. And then as I go through and satisfy the octet rules, I realize I need to add a lone pair on NH2, or on the N on NH2, rather. And then as a result, if I take a look and count them up again, 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, I have 20 in my structure. And as a result, I am done. Remember that carbons form those chains, and what we have at the end there is NH2, which is an amine functional group. We won't talk a whole lot about that today. But again, just writing them out and drawing them as they are written is going to be really, really helpful for you to understand how to draw complex Lewis dot structures. So let's talk about resonance structures, because sometimes more than one equivalent Lewis dot structure can be drawn. So let's look at ozone as an example here. If I go through and determine the number of valence electrons in ozone, it is going to be 18. Each oxygen brings 6 to the structure, so I have 18. Well, I can draw this one of 2 ways. I can either have the double bond on the left-hand side or the double bond on the right-hand side of this particular structure. So I can actually draw this one of 2 ways. Well, those are known as resonance structures. Now, one thing to keep in mind here is that this does not accurately depict the bond length or the strength that is present in this resonance structure. That is, this truly isn't representative of one double bond and one single bond. 50% of the molecules in a sample of ozone are going to have a structure that looks like what it is on the left, and then 50% are going to look like what it is on the right. So the reality is they don't behave as a double bond or a single bond, but rather behave as like 1.5 bonds. And I really want to make sure that you think about these a little bit differently. These bonds behave as 1.5 bonds. That is somewhere between the strength of a double bond and a single bond, as well as somewhere between the length of a double bond and a single bond. So be careful when you're looking at questions related to this, because in some instances they may ask you about the strength or the length of the bond here. If you're looking at a resonance structure, that does not behave as a separate double bond and a single bond. They behave both as 1.5 bonds. So it's somewhere in between the double bond and the single bond. So let's take a look here. We're going to draw out our Lewis structure for CO3 minus 2. And a student argues that the represented double bond in CO3-2 is stronger than that of the single bond in there. Do you agree or disagree with the student, and justify your response? So let's draw out this Lewis structure. And now again, I'm not going to go through all the complex steps. You should know by now how to go through and do this, but I count up the total number of valence electrons. 3 oxygens is 18, plus carbon is 22. We have a -2 charge there, so we're going to add 2 more electrons, so we're going to have 24 in our Lewis dot structure. So as I go through and take a look at this, I actually end up having a resonance structure. That double bond can appear on the leftmost oxygen, the uppermost oxygen, or the rightmost oxygen. So the 3 possible Lewis structures here. And the student argues that that double bond that's present in CO3 is stronger than that of the single bonds. Do you agree or disagree with the student? Well, hopefully, because you know that resonance structures, those bonds are not accurately depicted by the number of lines that are represented there. So hopefully, you would disagree with the student. CO3-2- is a resonance structure, which means that the 3 bonds are of equal length, even though they aren't represented that way in the Lewis dot diagram. Each bond behaves like 1 1/3 bond rather than a single bond or double bond, so they will have the same strength and same length. So resonance structures, again, even though they're represented by a double bond and 2 single bonds, they really aren't truly a double bond and 2 single bonds. They're all going to behave like the same length as the same strength, in this case 1 1/3 bonds. So let's take a look at formal charge. When multiple valid Lewis structures are possible, using formal charge calculations indicate the best possible Lewis dot structure. You don't see this very often because typically there is a 1 correct Lewis dot structure. When we calculate formal charge, we want as many zeros as possible when we go through and calculate this. So in order to calculate formal charge, we're going to take the number of valence electrons in the free atom. Again, that's what's found in the periodic table. We're going to subtract the total of non-bonding electrons. That is, we're going to subtract the total number of lone electrons that are on that particular atom in the Lewis dot structure. And then we're going to subtract the total number of bonding electrons divided by 2, or you can just subtract the total number of bonds that are attached to that particular atom. In this case, we want as many zeros as possible. If not possible, the best structure is going to have a negative charge on the most electronegative atom. So these are a couple things you want to think about as you go through and calculate formal charge. Let's look at an example here. So let's say I do some formal charge calculations with CO2. And there are really 3 ways I can determine CO2. We know that carbon has to be the central atom here, but I can use 2 double bonds on each side. I can do a triple bond on one side and a single bond on the other, or I can flip it and have a triple bond on one side and a single bond on the other. Well, if I go through and calculate the formal charges here, carbon has 4 valence electrons in its elemental form. It has no lone pairs attached to it and 4 bonds. So 4 minus 4 is 0. So carbon for each of these is going to have a formal charge of 0. If we have a triple bond on an oxygen, oxygen typically has 6 valence electrons in its outer shell. We're going to subtract 2 for the lone pair, so 6 minus 2 is 4. And then we're going to subtract the 3 bonds that are attached to it, so that's going to give it a +1 charge. And then if I look at the oxygen on the right-hand side in the middle, it typically has 6 valence electrons as well. We're going to subtract the 6 individual electrons that are attached to it. So 6 minus 6 is 0, minus the 1 bond gives it a -1 formal charge. So, and the same concepts are going to apply to the one on the furthest right there. But notice on the left-hand side here, all of the formal charges are 0. Those double bonded oxygens typically have 6 electrons when they're not bonded, minus the 4 lone electrons, minus the 2 bonds gives me a formal charge of 0. So as a result, the left-hand side Lewis structure is the best Lewis structure because all the formal charges that are calculated are going to be 0. So let's move on and talk a little bit about Vesper Theory, which stands for valence shell electron pair repulsion. Electrons in atoms connected to a central atom are going to want to repel as much as possible. This is due to the electrons in the outer shells not wanting to interact with each other. They're going to repel each other as much as they possibly can. Now, the diagram and the geometry of this is going to be dependent upon how many atoms or lone pairs are attached to an individual atom in the structure. So this results a variety of molecular geometries and shapes. Now, for this particular class, it's going to be important to know the first 3 rows here. That is linear, trigonal planar, bent, tetrahedral, trigonal pyramidal, and bent or angular as well. You're also going to want to make sure that you understand and know the bond angles that are associated with this. So how we go through and determine Vesper theory is based on two properties here. The first one being the steric number, which is the number of atoms or lone pairs that are attached to the atom that you're looking at. This is, again, based on the number of atoms or lone pairs. So it can be 2, 3, 4, even 5 or 6 if we're looking at some more complex atoms. Lone pairs typically reduce the standard bond angles by 2 to 3% for each lone pair that's added. So if you actually take a look at trigonal planar, which has a steric number of 3, you have 3 atoms that are attached to it. So for example, BH3, that would have a bond angle of 120, which makes sense because trigonal planar, it's on the same plane. And if you have 3 things attached to it, there's 360 degrees in a circle. So we would divide that by 3. So each angle is going to be 120 degrees. Well, those lone pair, let's say instead of having 3 atoms, we have 2 atoms and a lone pair that's attached to it. Well, that lone pair of electrons actually repels those atoms more so than an other atom would. So as a result, we actually get a bond angle that is less than 120. In fact, it's typically ranked around 117 degrees, about 3% less than what you would normally find in 120 degrees. So this chart's gonna be very, very useful for you to understand. Again, you're not going to actually get this. So it is going to be important for you to be able to memorize at least the first 3 rows. But as you practice with this more, this really does make more sense. The last thing I want to go through is what's called orbital hybridization, and it describes really the complex arrangement of electrons around an atom based on different types of bonds, as in sigma bonds as well as pi bonds. Now, I'm not going to go into too much detail on that, but what you do need to understand is that when these things bond, orbitals tend to overlap, and when orbitals overlap, they create unique types of orbitals themselves. And the way we know this is by looking at the steric number. So for example, if we have a steric number of 2, we would call the orbital hybridization SP. If the steric number is 3, it is SP2, and if it's 4, it's SP3. There are more than this, but you are not going to need to go through and know them. I would just basically memorize your steric numbers and your orbital hybridizations. Makes this a whole lot easier. So the last thing we're going to look at is a example problem where I'm going to ask you about the Lewis dot structure, the geometry, bond angle, as well as the hybridization. So to draw out the Lewis dot structure, again, I'm not going to go into too much detail in this, but phosphorus is going to bring 5 electrons to the table. 3 hydrogens is 3, so we're going to have a total of 8 in our Lewis dot structure. Attach everything to your central atom, which is phosphorus, and then add lone pairs to satisfy your octet rule. You count them up, you get a total of 8. So awesome. Our Lewis dot structure is very easy to go through and determine. I look at my molecular geometry. I have a steric number of 4 because I have 3 atoms that are attached and 1 lone pair. And I have a lone pair in there, so we're going to call this trigonal pyramidal because we have 3 atoms, 1 lone pair based on a steric number of 4. The bond angle here, a typical bond angle of with a steric number of 4 is 109 degrees, but because we have that lone pair in there, we're going to subtract 2 degrees from it. So as a result, the bond angle is going to be somewhere around 107 degrees. And then our hybridization, we have a steric number of 4, and that is representative of sp3 hybridization. So again, it is important that make sure that you've gone through the basics of this, because I've gone through this relatively quickly. But make sure you know the basics of how to draw your Lewis dot structures and understand how you figure out your geometry, your bond angles, as well as your hybridization. All right? So again, quite a bit we've talked about in this video. This wraps up our unit. But make sure that you are able to draw your Lewis dot structures, know when resonance structures occur and how that impacts bond strength and length, utilize formal charge, looking at Vesper theory to determine molecular geometry, as well as describing the hybridization on a central atom or any atom in general. Just keep these things in mind, that there's a lot that's going on here. There's a lot of uses of Vesper theory, not just with central atoms, but as you have long, complex carbon chains, you can determine the molecular geometry for a variety of different atoms in a structure. So just kind of keep those things in mind. Hope you enjoyed the video. Make sure you like, comment, and subscribe, and have a great day, and we will see you soon. Bye, everybody.